IoT data, contact us. We're proud to help manufacturers extract the value from the industrial Internet of Things.
Yeah, welcome back. Once again, thank you all for the patience, and particularly the president and convener at the Hyderabad Management Association and all the organizers. Good evening, all of you. Myself, Dr. G. Chandramohan Reddy, working as professor at CBIT, Department of Mechanical Engineering. I am giving this talk on smart digital manufacturing practices for SME sector in the global digitalization era. Yes, these technical glitches really hamper us, but it will not stop our resolve to proceed ahead to talk to all of you this evening. What is Industry 4.0 manufacturing? Some people say it is automation, it is data technologies, integration of software equipment and people. But the Industry 4.0 or the digital manufacturing brought in what is called as the transparency, right from the shop floor engineer to the top management. Every time, what we call is the digital thread, lot of data is generated as the process goes on. And you are also talking about digital thread and digital twin. Digital twin is not just manufacturing simulation, you are really connected to the real-time data. You are getting the data from the factory through the sensors, and it is integration of this virtual manufacturing with the real data. So that is called a digital twin. All these are happening, and you are going to see all those details. And this is also enforced, a kind of transparency that is very much required. That means you always point to the single source for the information. That is earlier not possible. And we should feel proud that India is part of this Industry 4.0 efforts across the world, not only in our country, everywhere, in every effort, Indians are participating in this mission. And then Industry 4.0, why it matters? Industry 1.0 is ordinary lathe, engine-driven lathe. Industry 2.0, from there we have moved to Industry 2.0 of fixed automated assembly lines of 1920s, where there used to be fixed automation. Whenever a car is manufactured, one engine is manufactured, that design used to stay for decades, the same design, same product. And that was the situation at Industry 2.0. From there, we have moved to Industry 3.0, that is called NCCNC, Flexible Manufacturing System and all. And now we are in the era of Industry 4.0. This is integration of cyber physical systems, Internet of Things, virtual reality, and all the several technologies that we are going to talk. So with this preliminary talk, and I am going to talk to you on these aspects today. This is the agenda of the meeting. What is digital manufacturing? Why do we need digital manufacturing? What is pushing digital manufacturing forward? Current state of digital transformation in manufacturing? What are the driving factors? And what are the opportunities and learnings? How can SMEs move toward achievable digitalization? What difference will this make to SMEs? Potential industrial products implications, potential consumer products implications, and the impact of Industry 4.0 on the complete industrial sectors worldwide. And this is where we have started. This is what we have seen when we are growing up ourselves in villages. This is a wet grinder that is used at home. And then from there, we have moved to this water turbine, right? And then from there is a flour mill. We used to go to carry the grains to the flour mill to make it into the flour to be used for domestic cooking purposes. And then from there is automated machines. Automated machines were also used. They were all there very much. And then all these eras we have seen. And then at this point of time, we wish to call What is digitization? Digital information from multiple sources, formats, different formats to address key challenges of society in various aspects such as health, education, water, transport, commerce, government and manufacturing sectors. Everywhere, a lot of digital information is coming from different sources. Then what is manufacturing? Manufacturing, there is a big M manufacturing, little m manufacturing. I would like to tell the difference. Soon after the independence, we were getting the technology imported. And in India, the industries were only manufacturing, means that is only activity in shop floor. There is not of, say, idea, innovation, creation. We have not put a lot of effort in those particular areas. So manufacturing is a process for converting ideas in the market. That is the bigger manufacturing. Little manufacturing is conversion of raw materials into useful products. The traditional definition, what you observe on the shop floor is where work orders and machine instructions are converted into hardware. The case of bigger manufacturing, converting ideas in the market or customer needs into artifacts includes design, procurement, test, finance, human resource, marketing, fabrication, assembly, and much more than this. So the artisan of history performed manufacturing. Then historical development of integrated manufacturing, you see the first industry 4.0, that was only manual manufacturing, and there was mechanization in industry 2.0, such as mass production, assembly line, electricity, all that of 1920s fixed automation to the level of programmed automation, and then automation, the computer and automation, and then integrated manufacturing. Integrated manufacturing, now we are calling it industry 4.0. When we say computer integrated manufacturing, it is not, that is in 90s and 2000s we spoke, that is limited up to there. But the real integrated manufacturing is integration with the cyber physical systems. And then with this, let us also have a recap of one more summing up video.
Welcome to the first course in the Digital Manufacturing and Design Specialization, Introduction to Digital Manufacturing and Design. My name is Ken English, and I'll serve as your guide as we explore this new approach to making products. After completing this lesson, you'll be able to explain what is meant by digital manufacturing, and also explain how digital manufacturing and design represents the fourth generation of the Industrial Revolution. To set the stage, let's take a step back to the first Industrial Revolution, ending in the early 1800s. This transition is often thought of as the Industrial Revolution, but is actually the first of an ongoing sequence. The first Industrial Revolution was represented by the transition from manual production to mechanical production, enabled by the harnessing of water and steam power. The second Industrial Revolution came at the beginning of the 20th century, with the development of approaches that enable mass production, including the assembly line. The third Industrial Revolution, also known as the Digital Revolution, represented the advances made possible by automation as mechanical and analog technologies gave way to digital electronics between the 1950s and the 1970s. We are now entering what is being described as a fourth revolution, also known as Industry 4.0. Industry 4.0 is the next phase in the evolution of manufacturing, combining the cyber capabilities resulting from advances in computing with physical systems to create a highly intelligent, interactive, and automated manufacturing ecosystem that integrates product design, manufacturing, and logistics. Now, a formal definition of manufacturing is the process of converting raw materials, components, or parts into finished goods that meet a customer's expectations. Manufacturing is the most tangible part of the product life cycle because it results in a clear outcome. There are multiple definitions of the product life cycle, most differing only in their terminology or details. For this course, we'll use the definition provided by Michael Greaves in his 2006 book, Product Lifecycle Management, Driving the Next Generation of Lean Thinking. Greaves defines the life cycle as all aspects of a product's life, from its design through manufacture, deployment, and maintenance, culminating in the product's removal from service and final disposal. The first stage in a product's life cycle is planning. This is where designers work through understanding requirements, whether they come from customer expectations, industry standards, or regulations. These requirements are then transformed into specifications, or technical requirements that can be measured. These specifications give you a way to evaluate initial feasibility of a product and whether the process should continue to design. Design is the product lifecycle stage where form and function come together to meet specifications. As you develop prototypes, whether physical or in a computer, design is where parts are created to fill the needs of the product. This begins in an abstract fashion with conceptual design and concludes with detailed design, where final, detailed part specifications are created. The next step of the process is to take the product from a design and build it. This stage includes when you define the items that need to be manufactured and how they'll be created and assembled. Production prototypes are created and checked to see if they meet performance and cost requirements, as well as long-term production capabilities are established. This is also where customers have a chance to evaluate the acceptability of a manufactured product. Once produced and purchased by the customer, the product must still be supported. The support stage of the life cycle is where you provide the customer with information to assist in the effective use of the product and maintain the operational performance of the product. A product's life cycle ends with disposal and recycling. The dispose stage of the life cycle draws on information from the design and build phases to understand the composition and what portions of a product can be recycled into future applications. As with other stages, the dispose stage may iterate with design as you work to develop a product that meets performance expectations and that can be disassembled at the end of life. Over time, multiple opportunities for improvement have been identified for traditional design and manufacturing processes. In a product's life cycle, many iterations may be required before customer approval is received. In traditional paper-based processes, information sharing can consume valuable time and delay the development process. In traditional processes, there is also a lag during and in between stages in the life cycle as necessary approvals are sought. Sometimes, this can even result in losing first-to-market competitive advantage. Another challenge in paper-based processes is that maintaining a single source of truth for product and process definitions is very difficult and can result in limited capabilities for data analysis and evidence-based decision-making. Communication problems can result when planned changes are made during design and development process, as well as after the production launch. A new approach is digital manufacturing. This approach uses increased computing power to improve the product life cycle. The Digital Manufacturing and Design Innovation Institute, or DMDII, defines digital manufacturing as an integrated suite of tools that work with product definition data to support tool design, manufacturing process design, visualization, modeling and simulation, data analytics, and other analyses necessary to optimize the manufacturing process. Deployed throughout the product life cycle, digital manufacturing enables you to more quickly and authoritatively share information in the design process, with all the data generated in every part of the life cycle representing a digital thread. This digital thread can be used to create a computer-based digital twin, an integrated system of data, models, and analyses that can be used in design, manufacturing, support, and disposal. These concepts all come together as the fourth industrial revolution, Industry 4.0. An example of the vision and promise of Industry 4.0 can be found in the wind power industry. Wind power is an important component of the clean energy industry. An ongoing challenge for wind farm operators is the significant wear and tear of gearboxes. Gearboxes are expensive to fix, especially after failure. However, if sensors on the turbine are linked with weather information and computational models, a very accurate simulation can be developed for each individual turbine, enabling evidence-based decision-making and the creation of predictive models for performance of individual turbines and the wind farm as a whole. This concludes the first lesson of digital manufacturing and design.
Yeah, that was the purpose of showing that video was to clearly show the simulation that was happening in digital thread and also in digital twin. This is how the industrial evolution has happened over a period of time. So this is, of course, and then there, of course, the particular years in which the industrial revolutions happened are 1760 to 1840 first, 1870 to 1940 was the second, 1960 to 2010 was the third one. 2010 onwards, what we are talking about is the Industry 4.0. See the Germany example, you can see the smart manufacturing leadership coalition with USA, a collective term of technologies and concepts of value chain organization based on the technological concepts of cyber physical systems, the Internet of Things and the Internet of Services. It facilitates the vision of the smart factory. Within the modular structured smart factories of Industry 4.0, cyber physical systems monitor physical processes, create a virtual copy of the physical world, and make decentralized decisions. Over the Internet of Things, cyber physical systems communicate, cooperate with each other and humans in real time via the Internet of Services. Both internal and cross-organization services are offered, utilized by participants of the value chain. So this builds on digital revolution, making use of the ubiquitous internet, smaller and powerful sensors, artificial intelligence, machine learning, labor, and it really results in saving labor and energy cost. See the technologies that if you see these were not their iPhone, iPad, Kindle, 4G, Uber, Airbnb, and Android. All these Instagram, Snapchat, WhatsApp were not there in the year 2006. If you see the time to reach 100 million customers, see telephone took 75 years and web took 7 years, Facebook for 4 years, Instagram 2 years, Pokemon Go just took 1 month to reach 100 billion customers. So this is how the evolution of the desktop right from 1980 to 2014. Then so far I have been speaking about the cyber physical systems. On one side you have the computation, the computer system, and the communication, and then control. So this makes the cyber physical system, CPS in short, is a system of collaborating computational elements controlling physical entities. CPS are physical and engineered systems whose operations are monitored, coordinated, controlled, and integrated by a computing and communication core. They allow us to add capabilities to physical systems by merging computing and communication with the physical processes. If you look at today's factory, they are all rigidly sequenced car manufactured and production line. If you see, after completing the operations at workstation 1, this will go to the workstation 2, and from there it will go to the workstation 3, and there to the workstation 4. It goes in a rigidly maintained sequence. If you see the tomorrow's factory, it is completely decoupled, fully flexible, and highly integrated manufacturing systems. They can go depending on the type of the product. The sequence depends on the product. It will go in any fashion, A to H, H to K, or something like that, X to H to T, something like any direction it can go depending on the sequence which is required. Industry 4.0 essentially consists of 6 design principles: interoperability, the ability of cyber physical systems, that is workpiece, carriers, assembly stations, and products, humans and smart factories to connect and communicate with each other via the Internet of Things and the Internet of Services. Maybe, sir, Mr. Karthik, with your kind permission, shall I try slideshow at least once from here after? Mr. Karthik or sir, Rajendra Garu?
Ramchandra garu co-host, ఆయన చేయొచ్చు మీకు.
You can do it, sir. You can please do it. Slideshow, you can go ahead, sir.
అంటే ఇట్లనే వెళ్ళమంటారా లేకపోతే స్లైడ్స్ నొక్కమంటారా?
ట్రై చేయండి సార్, మంచిగా ఉంటుంది. బికాస్ ఫుల్ స్క్రీన్ వస్తే విజిబిలిటీ విల్ బెటర్ కదా.
అదే నేను ట్రై చేస్తున్నాను సార్.
ఎస్ సార్, ఎస్ సార్, ఎస్.
వచ్చిందా సార్?
రాలేదండి. Gone out.
అది తీసుకోవట్లేదు.
Can you continue, sir? Better continue.
యువర్ స్క్రీన్ షేరింగ్ ఇస్ పాజ్డ్ అని వస్తుంది నాకు.
Go back, sir. And go back and
సో ఎస్కేప్ కొట్టి బ్యాక్ వెళ్తాను, చూద్దాం. అది గ్రాఫికల్ లోడ్ తీసుకోలేకపోతుందండి, బికాజ్ ఇట్ ఇన్వాల్వ్ లాట్ ఆఫ్ గ్రాఫిక్స్. నౌ ఇట్ ఈస్ ఓకే అండి.
Fine, sir. You can go ahead, sir. Because when you are not able to do this, okay to manage this.
Okay, sir. Yeah, the 6 design, one is interoperability, next is virtualization. A virtual copy of this smart factory which is created by linking sensor data with virtual plant models and simulation models. That is ultimately leading to the digital twin. Then is the decentralization, the ability of cyber physical systems within smart factories to make decisions on their own. Real-time capability, the capability to collect and analyze data and provide the insights immediately. Next is the service orientation, offering of services via the Internet of Services. Modularity, flexible adaptation of smart factories for changing requirements of individual modules. Then there is what is called as number of building blocks of Industry 4.0. If you see, there is big data analytics one side, and then autonomous robots, simulation, horizontal and vertical system integration, industrial Internet of Things, cyber security, additive manufacturing. See, the manufacturing is one area where whatever the revolution that is taking place in computer science and electronics will have a profound effect on manufacturing. Manufacturing is one area which is capable of absorbing any kind of technology, the advancements that are happening, particularly in electronics and computers. Most of us think that manufacturing is a mechanical engineering core area, but certainly the developments that are taking place elsewhere will have a.
The Internet of Things has the potential to increase global productivity up to 25% by 2025, which could translate to an economic value of $11 trillion. Industries like manufacturing are embracing the potential of the Internet of Things. Many production facilities are already using processes and supervisory control systems with connectivity. The Internet of Things for manufacturing is a family of solutions that combines the capabilities of analytics, cognitive computing, and the Watson Internet of Things platform to drive operational efficiency across the factory value chain. This solution benefits the manufacturing industry in 3 main ways. First, it helps plants get 100% efficiency out of their equipment by identifying and solving issues before they cause delays. Second, it makes processes and operations cognitive, so plants can produce maximum quality and yield from raw materials and manufactured components. Lastly, the Internet quality standards along the production line. Simon uses a quality analytics tool to identify variability in the manufacturing process in real time. This allows equipment operators to make adjustments to process parameters based on plant conditions that could affect the quality of production. By monitoring quality in real time, Simon's team can avoid producing faulty components, ultimately saving time and money. Another priority Simon has to account for under a rush schedule is the safety of his plant workers. The cognitive heat or toxic gas measures if physical well-being is compromised will be able to safely take on an accelerated schedule and make plans to move forward. Once the completed aircraft from Simon's plant is put to use, those manufactured parts continue to generate data over time. Data that designers and engineers can use to make improvements also make it possible for Simon's plant industries will improve the way they design and manufacture connected products. Products that will change the way we work and live.
This is a factory smart connected. So what you are seeing is the inside activities, particularly the work is being moved from the kind of devices and the machinery and the vehicles that are being used. Okay, these are all the building blocks that I wanted to show, and they are to be tackled, and it will have a profound effect on what is it to come in the, and all these impacting all aspects of the value chain, as the manufacturing is going through several aspects, right from the design, creation, innovation, planning, then implementation. When this is happening, so this will impact the engineering, design tools and simulation, the life cycle data management, digital manufacturing, industrial control systems, sensors and actuators, maintenance and repair, asset management, industrial communication. These are all the several aspects which are getting affected. Maybe this is also explained with the help of a small video.
Distributed organizations are involved. Let's consider something simple, like this pen. This pen is a BIC Pilot G2. BIC is the organization that manufactures the end product, what we purchase. A term for BIC's place in the enterprise that creates this pen is the OEM, the original equipment manufacturer. The OEM relies on suppliers to manufacture and deliver components that can be assembled. These suppliers purchase component parts from other suppliers. This can repeat many times, getting to the most basic components of a product, like the ink in this pen. These suppliers are referred to as Tier 1 suppliers or Tier 2 suppliers, etc., referring to their place in the structure that provides components that are assembled into the pen. The supply chain refers to the system of organizations involved in creating a product. Products of any size have a supply chain. Consider the Boeing 777, a very large and complex airplane. As the OEM, Boeing manufactures the final product. In order to manufacture this end product, Boeing purchases large shock-absorbing assemblies from a Tier 1 supplier, ITT Enidine. ITT Enidine purchases machine pistons from a small machine shop.
This digital thread and digital tinning is going to be extremely useful
to enhance surface properties.
across the value chain,
and
the
plating
OEM
shop
to
are
Tier
examples
1
of
and
Tier
to Tier 2
suppliers.
everywhere, because they
Next,
always
we
look
have
to
two
the
videos that highlight concerns that can result from a complex supply chain. Please watch the videos and take a moment to consider their impact. For the 777 to be manufactured with the right quality, in the right amount of time, and at the right cost, it is critical that all organizations in the supply chain communicate effectively. This communication includes timely information sharing with the right stakeholders. Rather than relying on paper documents, a digitally enabled supply chain allows design documents, part revisions, and purchase orders to be shared electronically. Redesigned components can be checked for fit without having to produce a single part, saving significant time. A way to think about this impact of the DMD paradigm is the right data in the right place at the right time, enabling quick and correct decision making. This focus on the timeliness of data reduces the impacts of a change that can lag in time and grow in scale as it propagates through the system. Sometimes this is known as the bullwhip effect. An example of this is how
the purpose of that video is to show you how the digital manufacturing is going to be useful, not only the OEM, across its supply chain. Supply chain is the one which adds value to the chain. Therefore, I coined it as value chain. Then in the digital enterprise that we are talking about, the entire value chain is digitized and integrated. On one side, you have the digital world. On one side, you have the real world, and you have the simulation. The product lifecycle management is right from its creation to its disposal. That is called the PLM. Manufacturing execution system that comes from somewhere around the planning to its manufacture and testing. And then the actual factory operation is totally integrated automation. And the life cycle and the data-driven services come somewhere here between 3 and 5. So therefore, digital world, the real world, it is connecting through product design, production planning, production engineering, production services. And when the component goes into the market, there is going to be a lot of feedback that comes and that can be shared across. All this is enabled by digital manufacturing. And of course, as mentioned, there are 7 real world examples of digital manufacturing. Making use of the industrial Internet of Things broadly refers to a series of internet connected sensors, devices that provide real-time data from across the factory floor, allowing for improved visibility for machine performance. Next is big data and analytic tools help translate big data into actionable insights that are then used to project demand forecasting and predictive maintenance schedules. Then cloud computing allows for over-the-air transfer of real-time data. Everybody in the line product lifecycle can access it to the single source only. Always it is only the single source to which everybody can access. Next, advanced robotics allow for automation of increasingly sophisticated tasks. Next is additive manufacturing allows for specialized production of unique or customized products and components. Customized products means one customer, one product. It is possible making use of the additive manufacturing. Next, digital thread and the twins gives manufacturers a view of the entire factory floor in a virtual space. Sitting across the computer, you can see what is happening in real time. Augmented reality, AR, can provide asset status, performance, or task specific information at a glance. Potential implications of this one is robot assisted production, predictive maintenance, additive manufacturing of complex parts, machines as a service, big data driven quality control, production line simulation, smart supply network. So with the increase in the robots working in the suppose this is only one example, of course from 2013 to 16 the number has increased. The main reason is the digital manufacturing. Some examples: Siemens, German manufacturing giant Siemens, an industrial user, is implementing an Industry 4.0 solution in medical engineering. For years, artificial knee and hip joints were standardized products, with engineers needing several days to customize them for patients. Now, new software and steering solutions enable Siemens to produce an implant within 3 to 4 hours. See, here it is like this. Every customer requires a unique knee joint, knee and hip joints. No two customers are same. No two patients' requirements are same in this particular aspect. This can be met effectively with the digital manufacturing and design, with the kind of additive manufacturing. See, additive manufacturing really is amenable for implementing in digital manufacturing. The scope for implementation of digital manufacturing increased with the additive manufacturing. Next is the Trumpf. This German toolmaker Trumpf, an Industry 4.0 supplier and worldwide market leader of laser systems, has put the first social machines to work. Each component is smart and knows what work has already been carried out on it. Because the production facility already knows its capacity utilization and communicates with other facilities, production options are automatically optimized. The next example is GE. Predicts the operating system for industrial internet is powering digital industrial businesses that drive the global economy. By connecting industrial equipment, analyzing data, and delivering real-time insights, Predicts-based apps are unleashing new levels of performance of both GE and non-GE assets. Next, evolution of product and process design. If you see, 80s, you're visualizing the design in a drawing. And then over a period of time, you're seeing it, you have computer aided, and then seeing it. And then next stage is assembling them and then seeing them in the simulation. And then you have moved to a situation where you are integrating with the real-time data and then seeing in the form of a digital twin. Examples of product evolution. See, products, even control aspect has gone up like anything. See, users, Philips lighting you take, users can control Philips lighting light bulbs via smartphone, turning them on and off. Of course, this is very much known examples. There is another device called Meditronics. Of course, there is a saying, coming together is a beginning, keeping together is progress, working together is success, by Henry Ford. Yeah, is digital manufacturing new? I wanted to put one question at this juncture. Digital information from multiple sources, formats, owners, etc. for the enhancement of manufacturing, you termed it as digital manufacturing. It is happening in different forms. In 1990s, the application of digital information for the enhancement of manufacturing processes was done. In the year 2000s, the application of digital information for the enhancement of manufacturing processes and supply chains. 2010s onwards, the application of digital information from multiple sources, formats, and owners for the enhancement of manufacturing process, supply chains, products, and services is being done. Now, if you look at the engineering processes for product realization, right from the product requirements, specifications, design synthesis, design representation, design analysis, design evaluation, manufacturing planning, manufacturing execution, and then inspection. So there are several iterations that are required to be performed to ultimately realize the product. Now in this, who casts the biggest shadow here? See, product design, see, if you look into the cost, product design cost is only 5%, material cost is 50%, and 15% is the labor, and 30% is the overhead. But if you see the influence on the product design cost-wise 5%, but its effect is much more, 70%. Material cost is 50%, but ultimately its influence is 20%. Labor cost is 15%, but their influence is 5%. Overhead effect is 30%, it is 5%. This ultimate key is the product design, the innovation, the idea. It is the one which is the biggest shadow in this whole process. The big threes in a production cycle are design, production, and then the process planning. Of course, these are the activities in a production cycle. The design operations, there are planning operations, there are production operations. So design, see, same thing is being done in a CAD/CAM integration. This becomes like this. So design operations were taken up by the CAD, planning operations are grouped into CAD, and production operations are CAM. So in digital manufacturing technology, CAD/CAM is given a name, virtual prototyping. You will come across those terms, virtual prototyping and virtual simulation, and integration with the real-time data happen to be the digital twin. So that difference, I think, boundaries between functions in traditional manufacturing, the business and production, there are clear-cut boundaries between engineering and human resources everywhere. But there is a lot of redundant data also. See, the data that is available in the business cannot match with the available in the production. Sometimes it will not match with the information that is available in the human resources. So you are not referring to the single source in all these things. Everybody will maintain their files separately in the traditional systems. They will collect, they will maintain. Redundant data cause manufacturing problems. There are going to be problems of, see, because of when they're not equivalent, they are not accurate. How to make, say, engineering to additions, deletions, changes, and then file. So there are hell lot of differences that are going to arise in traditional systems. This redundant data cause manufacturing problem. information flow from design to production shop. See, there is a tool design to the, of course, ultimately it is the product design to which the tool design work and tool design goes to the manufacturing. And of course, you again get the feedback, and once again it is incorporated. This flows like this. Of course, this is a known thing, but the sharing of the information, this is very well explained in this particular video. You can see this. Information sharing is very key.
As we continue working through a high-level view of the digital manufacturing and design paradigm, we get to the topic of how information gets shared between groups, whether machines, suppliers and manufacturers, or customers. After the lesson, you'll be able to explain the role of data and purchasing communication standards in manufacturing and design, including real-world scenarios where these standards can be applied. Why are standards relevant? Why do we need to be aware of the technical details of transferring information? Consider a simple example, a single manufacturing shop floor. The shop floor has several computer systems and manufacturing equipment of varying ages, each generating different output. The individual pieces of equipment are creating data in different formats for various reasons, like systems from different manufacturers have output in proprietary formats as part of an effort to lock in future software and hardware purchases. However, if we need to establish a relationship between two different data sets to create information or connect machines from different manufacturers, they cannot be in different formats. That's what data standards do. They specify a consistent data format so the data can be shared and transformed into usable information. Some examples are STEP and IGES are data standards for sharing product design data like geometry.
These are the file formats in which it is
MT
shared.
Connect is a
MT Connect
standard
is a
that
standard.
supports the capture and sharing of information from machining equipment. MIL standard 31000A and ASME 1441 define a way to share technical data package to support the product lifecycle. To complete learning about standards and their place in the digital manufacturing and design paradigm, we're sharing two additional items in the resources section. The first is a video on MT.
Next, in the traditional manufacturing system also, you try to maintain the common database, but that never happened. But this is happening only in digital manufacturing system. That single sourcing, availability of a single source information everywhere is made possible in this one. So common database you try to create, but when changes occurs, it becomes very difficult to maintain. So and of course, once again, the cyber physical systems definition I have put to remind you that it is cyber, the internet, the networking through because of which you are able to have the single source information. Then the life cycle considerations in product design. These are all the working conditions, resource optimization, life cycle costs, company policy, product properties, and then ease of manufacturing, environmental protection. The life cycle design, if you see, these are all getting affected. These are all have got the profound effect on the life cycle design, right from the creation of the product to its final disposal after use. So now the manufacturing trend has changed, wherein you will have to design right from creation to its disposal, which you are calling it as life cycle design. All these have got the effect on the life cycle design. And people are moving more towards mass customization from mass production. So without much increase in the cost. So even if from mass production to mass customization, the difference should not be more than 3 to 5%. But through the mass customization, you are going to satisfy each and individual customer, which is not possible through mass production. In this also, you are going to create large amount of data, and there is a rapid sharing and the processing of data involved. So this is another curve showing mass production versus mass customization. The present generation is moving towards more of mass customization. Mass customization has the ability to produce a single and customized product with the same efficiency as a mass produced product. Now this is happening in a big way. And regarding the impact of Industry 4.0 on several aspects, one is the impacting the economy in terms of growth and aging of the world products, the productivity, the employment, labor substitution, and the nature of work is also changing very fast. And it is also impacting the business in terms of the customer expectations, data enhanced products, collaborative innovation, and new operating models. And workforce, if you see now how it is affecting the workforce, you see this video.
Transition from traditional manufacturing to a more integrated digital approach will impact the workforce. After this lesson, you will be able to better understand how DMD will impact the workforce and career opportunities. In manufacturing, the workforce has evolved over time, following along with the industrial revolutions. First, as artisans who handcrafted entire products one at a time. Then, as a skilled workforce, specializing in individual components of a product, like the suspension system of a car. Eventually, workers are seen as a blended workforce, where the focus continued to be on the manufacturing skills an employee might have, with some post-hiring training in continual quality improvement, like understanding the principles behind Six Sigma, or learning to operate multiple machining centers to increase efficiency. Operators are still seen with an open-loop perspective. The focus is on my machine, just processing materials to generate output, without any opportunity for feedback to impact the end product. Digital manufacturing and design envisions a workforce highly engaged with the creation of the product. From invention through to disposal, workers will need to understand how their actions impact design, manufacturing, and logistics. Workers will also need to use analysis tools and advanced machining to efficiently produce products, especially in a mass customization environment with a high mix of products, each with a smaller batch size. These changes shift the focus for digital manufacturing and design from only tooling and machining skills to workers that also have skills in technology, operations excellence, and people skills, or the ability to effectively collaborate with others as part of a team. Some items to keep in mind when considering the impact of the digital manufacturing and design paradigm are: the National Institute of Standards and Technology, or NIST, estimates that 600,000 manufacturing jobs are unfilled in the United States because of the lack of high-tech manufacturing skills among job seekers. According to the Society of Automotive Engineers, SAE, over 98% of all products will be developed digitally by 2020, which makes this skills deficit even larger. Small and medium-sized enterprises, SMEs, consisting of 1 to 500 employees, represent 95% of our nation's manufacturers. But 94% of SMEs have not adopted high-performance digital manufacturing practices. All this means that the opportunity to create a new generation of a workforce that is excited about and competent in digital manufacturing and design methods is very real. This shift may result in changes in job titles. Manpower is working with the DMDII to identify and update job titles impacted by Industry 4.0. Titles and responsibilities for drafters, CNC programmers, machinists, especially those using manually controlled equipment, document control specialists, inspectors, and testers performing visual and manual inspections will all change. Not all current job titles will be impacted. Tool and die makers, as well as inspectors for highly critical items that just cannot be inspected by digital means, will have minimal impact. Additionally, new job functions will be created. Others will emerge as the Industry 4.0 revolution continues. But we do know there will be a need for employees with skills in advanced manufacturing, agile, robust, integrated manufacturing, modeling and simulation, including model-based systems engineering, or using the digital thread to minimize multiple designs or prototypes or test iteration, intelligent machines, using self-aware manufacturing hardware, smart sensors and controls to develop instrumentation for legacy equipment and use big data analytics. Advanced analysis. These are jobs in high-performance computing, design for manufacturing, integrated smart design tools that reduce over-engineering. And finally, cyber-physical system security. These are trusted networks, gate and IT controls, or ISO 27001. The DMD revolution is going to open up even more opportunities for a skilled workforce, creating a market for higher paid workers who use their knowledge to impact the creation.
So now it is open for MSMEs to really adapt the digital manufacturing in a big way, as that is very much clear in US scenario also. National and global, it is going to impact governments, countries, regions, international security, inequality, community, the individual identity, morality, ethics, and human connection. So this is another area requiring deliberations. Top 10 skills to be relevant. Of course, in 2015, these were relevant. Problem solving, coordinating with others, people management, critical thinking, negotiation, quality control, service orientation, judgment and decision making, active listening and creativity. In 2020, complex problems. 2020 anyway, it got dragged to 2022 to 23 because of COVID. So we can still consider this complex problem solving, critical thinking, creativity, people management, coordinating with others. Emotional intelligence is another one, which is not there earlier. Then judgment and decision making, service orientation, negotiation, cognitive flexibility. This is another one. So there is another kind of small video for data security and disaster recovery. This is another area which is also to be looked into for implementing.
All of this content, the worst thing that can happen. Instantly came to mind. Dig deeper. That's probably not the worst thing that can happen. With 1 foot in the world of information technology and 1 foot in the world of mechanical engineering, I have a fairly unique perspective on the lessons to be learned that make the adoption of the digital thread possible. In the information technology world, there's a large focus on security and disaster recovery.
So this video, the purpose is to say that there are extreme cases, natural or man-made also disasters. So therefore,
the good news
how to
is that this is
create this particular disaster management core team, how to create it and maintain. This is also to be looked into.
Cybersecurity is relevant.
That's I want to emphasize. And finally, it's the vision for implementing the digital manufacturing and design. So please.
As discussed. People can even come to ask, how do we stay in touch? Now combine that thought with the idea of seamlessly sharing information throughout the life cycle of a complex product. Large integrating manufacturers, or OEMs, will expect that all of their suppliers use technology to increase efficiency and effectiveness. In fact, these requirements are already being incorporated into the bidding processes for contracts. Those who are not digital need not apply. This module focuses on the ideal digital manufacturing and design world, with an ever-present digital thread at its center. Some years ago, there was a Defense Department program review where one of the attendees stood up and mentioned that now that there was a requirement to use a digital technical data package, or TDP, the number of bidders dropped by 50%. That means that just based on the conditions of the contract, even if they produced a world-class product at a great price, some companies just could not compete. And that was quite a few years ago. In many areas of industry, the digital thread is well on its way to adoption. As with other advances like supply chain management and Six Sigma, once the benefits are known, others will adopt the innovations as well. Many of the components of the digital thread will be incorporated like trade secrets. Competitors will just get faster and produce better products. At the same time, companies are increasing the expectations of their employees beyond manual labor. When I say manual labor, this doesn't just include physically lifting equipment and products, it also means controlling equipment like machining centers. A reality that exists is that manual labor costs are lower outside the US, making going offshore an option to companies that look at keeping unit production costs low. Instead of lowering labor costs, an alternate approach is to increase productivity, producing more products with the same workforce, often with some form of automation. This relies on the willingness of the workforce to innovate, adapt, and take more responsibilities within the production process, both in design and in manufacturing. In the next lesson, we'll introduce the diffusion of innovation and give you the opportunity to assess where you stand on that spectrum. Understanding the world and where it is headed is the first step in adopting the digital thread.
That is the end of my presentation, but that is not the end of the digital manufacturing, right? So now it is over to the organizers to conclude. I mean, to invite
Fine.
some doubts or clarifications from the viewers.
Sir, I think it's a very high-tech presentation as such, I can say that.
Actually,
we are standing in India. There's, in automobile side, engineering side, or a defense manufacturing, or some sort of a machine tool manufacturing, or we are able to set up this, or we become any global players in this particular line, sir? Or what exactly is the hurdle for us to get up in some components, some technologies, in a global, to become a global player? What your projection on that particular part of it? Government is ready to help, like in providing finance and everything to them. But
Yes.
people, how entrepreneurs has to get up to that competitive levels.
Yeah, the question is, unlike the earlier industrial revolutions, this industry 4.0 is highly implementable with the kind of technologies and our participation, particularly in IT. Our participation is there in a big way. But earlier to that, we were not there. But because of our role, right from the stage of the development, right from the innovation creation, our participation was always there. We are maybe at par with our counterparts everywhere in the world, sir. Yes, it is implementable, sir, everywhere. Locally also it is implementable. Yes.
And then you quickly has to adopt this technology in faster way, and then it should be some sort of a global supply chain. What, to my knowledge, sir, like today in an economical point of view, you mentioned in one video that's airborne manufacturing thing. They're able to looking for supplies. One person may not be doing it in a very faster way. Definitely, we call it the vendor development or supply chain management. People are looking forward for supplies in a global level. Today, this
actually, that is what is the industrial internet of things. We have the app. Mere app lo chuskuntaru whoever is ready to supply that particular item, whoever is available, you will take from him. Actually, today it so happened that two of my colleagues bought same cars. That Tata Nexon. ఒక ఆయనకి ఏమో ఇది బ్రిడ్జ్ స్టోన్ టైర్స్ ఉన్నాయి, ఇంకొక దానికి ఏమో ఇంకొక టైర్స్ ఉన్నాయి. Then we were discussing why the same car manufacturer using two different brand tires. These two cars are purchased on the same day.
Okay.
So finally we came to know that it is because of the supply chain management. Supply chain, whoever is ready to supply, the order is placed on them.
But standardization is there for the
Yeah, of course. That standardization and qualifications are to be there. Only the qualified people only they will be placing the orders. Yeah.
I think Ramchandra Garu, I think he can summarize our next proceedings, sir. My part is over.
Sir, Ramchandra Garu, unmute
sir.
Thank you, Ramchandra Garu, for guiding me, especially when there was a technical issue was there.
Yes, sir.
Yeah, very quick to guide me. Yeah.
Thank you, sir. Thank you. Nice of you, sir. I felt that this is basically a wonderful introductory session to most of us, sir. I think there may be some quite competent people who probably have the exposure to this particular technology, the IIoT. And sir, you brought out the various facets of this particular thing very, very well. So I have a question to you, sir. I just wanted to know, just the speaker there, whom one of the videos where you put in, said even in an advanced country like US, you find that the SMEs, which nearly contribute to nearly 95% of the production, industrial production, 90%, 95% of the people have not adopted to the industrial revolution. Even industrial revolution 3.0 also. Very few industries probably went for advanced mechanization or even integrating with the IT. Now, what are the barriers? This obviously says that there are huge barriers for the SME sector to get into this particular IIoT 4.0. So, sir, can you please tell something about it? And second thing, sir, as I see, in fact, I am also a mechanical engineer. And when I did about almost 30, 40 years ago, when I was the shop floor, the most modern time in those days was a copying machine. HMD had a pilot machine, and that was a copying machine. Then came the NC machine, and then later on, let's say a lot of NC machines did come. But in India, we don't find that in advanced technology using robotics, except probably in few automobile companies. I think the SME sectors, are they geared for this sort of technology and the existing machines are normally not so very robust? Can retrofitting be done to see that they become compliant to this IIoT, sir? Is it possible? And one more question, I put a lot of questions, sir, but because you've been talking so wonderfully about this, I'm tempted to ask one more question is that in India, can you tell, sir, which of the companies are really adapted to this IIoT already? IIoT, whether in the SME sector or in the large sector? Doing it?
Bosch is the one that is implemented. Bosch is one company that has implemented. There are few biscuit factories, sir, where we have implemented this in India. A few biscuit factories, but I have to get the details. These are some of the case studies. I obtained through some of my students when I gave them the assignments to study. So these two details only they brought very recently. But worldwide many. But in India, Bosch and some biscuit companies, biscuit manufacturers are there. Yes, sir, it is happening. But to what level it has happened, it may not be clear, but it is happening here also.
Sir, in the process industry, like, if you say pharma industry, drug industry, or some sort of cement industry, process industry, SCADA is one software, they are using it, and it has been there. You can see a lot of good multinational companies or good-based companies, petrochemicals or any process-based industry, they are adopting the SCADA in the process application, and they are able to monitor the quality levels and going for 6 sigma in the manufacturing. That particular part is very good, is happening. Whereas coming to the engineering industry side, we have to gear up. What type of things we have to inform to the government at least, so that they are ready to help us. A lot of SMEs, how to do it, and they are ready to finance it, they are ready to come with a lot of schemes. But how these entrepreneurs has to be helped out, like technology transfer to be done, or education to be given, or training to be given, or innovation R&D to be implemented. What exactly it's a thing is, we have to come out with some sort of a points and address it to the government, so that
Sir, actually the question here is most of the time we always resist the changes, but change is the one which is required very much. But everybody knew it, but in practice, to implement it is a mental block, sir. Actually, physical problems can be overcome. This mental blocks, this attitudinal changes are required because the change is the order of the day. Unless we change Once the change, yes,
Yeah.
then the implementation aspects can always be looked into. Yes, sir.
Sir,
You're
I
right,
think
you're right.
Mr. VSR Garu, I think he is asking, he raised his hand, sir. Maybe he would like to talk.
Yeah, yeah,
Ask a
please.
question. Yes, sir. Please, sir. Srinivas Garu. VSR Garu. Sir,
Hi,
yeah,
sir. Yeah. Yeah, I think change management, I think we are talking is not easy. As you rightly said, we have been struggling in all aspects of life, whether it is
Sir,
society.
audible లేదు సార్ వాడు ఏం చెప్తున్నారు. హలో, am I audible, sir?
Yes, sir. Yeah, please go ahead.
బట్ వారు ఏం అడిగారు నాకు అసలు వినపడలేదు సార్. మేబీ
No, he says that he was saying that the change management is very critical, and I think probably he has to continue. Sir, Srinivas
Okay.
Garu. Yes.
Yeah. So
వారిది నాకు వినపడలేదు, మీరు విని నాకు చెప్పండి సార్.
okay.
That's better.
All right. Okay. So change. Okay, change is inevitable today.
వస్తున్నాయి మనకి, అదే ప్రాబ్లం.
Probably Ramchandra Garu, you can communicate to him.
Yes, sir. Please.
Okay. So what I'm saying here is today there is no choice except including MSMEs or big organizations have to become digital. A lot of new technologies needs to be embraced. But unfortunately, small and mid-sized companies, they always feel that it is very expensive and not affordable. And probably we can wait for some more time. And by that time, next 3 years, 5 years, they may extinct. So what is the best way? Is it something you can cluster them and ensure that the cost is shared among these MSMEs? So how the digitalization initiatives can be accelerated in the MSME phase, because there are so many constraints, number one. And number two, some of the MSMEs are driven by heroic efforts like 1 person, 2 persons driven. And I have tried some change and it did not work, because they believe that the way they have been doing is the way they have to do even today's era. If it is an organization, it is somewhat easy, but if it is 1 person, 2 person driven, it is very difficult. In these scenarios, how you accelerate this smart manufacturing and all is a question.
Sir, I don't know whether Chandramohan Reddy Garu has heard him, sir, but I think his questions are very clear. And what VSR Srinivas Garu, sir, I don't know VSR means. I hope.
We Srinivas Rao.
Yes, sir, please.
Yeah.
So actually, what I think he was saying, sir, which I think probably I also asked the same thing, the barriers for SMEs. Now, even in the lecture that the gentleman gave, also mentioned very clearly saying that 94% SMEs, even in US, where it is supposed to be an advanced country, you don't find the adaptation to the technology. Now, what the sir is saying, Srinivas Garu is saying is that even today in India, apart from the change management, which always puts a big break, the point he says is can at least some clustering can happen for similar activities where probably they can use this technology, which probably normally is expensive, and will they be able to adapt it? So what are the ways out? Perhaps that is probably his final answer question. What could be the way out? And I'm also adding a little more to that, sir. Is India geared up to this sort of thing where our SMEs are much more, like what sir rightly said, is that a one-man army, 1 or 2 man army, that's all. So, he has to run around for everything, and I don't think he's so competent. Even the workforce also, are they competent technically? So, India, as you again also point out, say 3 years, 4 years later, if the companies become extinct, a newer technology may come and overtake this particular thing. So, I think India is facing definitely a constraint on this aspect. That's my observation, sir. Maybe you can clarify, sir, please.
Yeah, I think VSR గారు ఏదో అడిగినట్టున్నారు. నేను అప్పుడు మీటింగ్ నుంచి ఎగ్జిట్ అయ్యి మళ్ళా జాయిన్ అయ్యాను. సార్ ఐ థింక్ మీరు కొంచెం రిపీట్ చేస్తారు సార్.
No, sir. Actually, what Srinivas Garu was asking was, which was an extension of my question, which I raised earlier, that even in America, where the technology is supposed to be advanced, 95% of the people are not adapted to the newer technologies, IT-based technologies.
Yes.
Very few companies are there. Even in India, naturally, the particular level would be much lower. SMEs in India are always constrained heavily for several factors. One is credit, one is finances, and then again, finally, it's a one-man army. So Srinivas Garu also is asking the same thing. It is a one-man army, easy, readily capable of doing this. Can there be a clustering of people? Probably they can come together and adapt this technology.
Yes.
There are similar products that could only be possible. And I was asking
actually the companies
how many people can afford this?
The companies are, especially in Institution of Engineers, in one of the lectures I have seen some of the same topic when discussed. the small scale industries people, particularly 2-3 manufacturers in Challapalli and 2-3 manufacturing people from Bangalore coming together and then discussing on implementation of a smart connected factory. Of course, a segment of the industry 4.0, but they are into it, sir. They are upgrading themselves in terms of understanding what exactly is happening elsewhere. But they are aware. They are aware, and they will come to know that it is going to impact the manufacturing, and they are readying themselves. I mean, a year ago, I think I was also participating in that discussion. Our SME people are also, I mean, they are aware of the international changes and they know the subject aspect also. Only the question of implementation. I've been mobilizing, of course, how it is going to impact their economy, how to mobilize the finances and then implement it is only the thing that is to be looked into. But otherwise, mentally they are preparing actually. I was also there in those meetings. Yeah, please.
I just want to add actually, sir, for this particular,
Yeah.
like the root cause, if at all you go back, like after getting independent and all, our engineering, our policies are all make for India, use in India, and consume in India for especially this engineering type of products. That was the concept. When we went to the recession part of it, 90s, then there is no other alternative because one ambassador only were depending on one Alvin or fridge only depending on such things were happening at the time, and no one in monopoly take up of attitude was there in entrepreneurs, and they were not really gearing up in the global competition. When economic crisis has come during the time, we opened up the economy to the globally, then we had to invite, we signed it in the pact and a lot of foreigners, a lot of foreign products are coming, and all automobile industry, machine tool industry, white goods industry, everything is washed off. Because why? They're already advanced in the product design, innovation, and again manufacturing process. Everything was went ahead of it. We are only having an assembly units producing whatever they want, and they are monitoring it and they are selling the product. That was the scenario at the time, and it keep coming. A lot of our people have been closed. Only one or two automobile people. One is in Bajaj, other is Mahindra, and other is Tata. These three people are just sustaining it and they try to gear it, but still it is not happening. Because again, in automobile also, a lot of multinational companies, with their innovation in the product design and manufacturing technology and practices, they are coming it up and just giving us the assembly unit because we have a population, we have a good trading and marketing places, so they are giving to us. And this was the, but luckily IT point of view also, IT we are only got help because US looking at the time evaluation of a 2K side, they're looking for the people who can help out. So they picked up the good brain drain from India and they trained on the IT and we are getting the services base of IT product. We are not having any IT product. We are not having any engineering product. Now, only option in the digital 4 and future digital 5 opportunity is that we are going for 4G now and future we are going to 5G. The technologies will be adopted and available and the best logistics and best supply chain the concept point of view. We people can gear up and government also realizes that and the rise the capital funding and interest rate to the employees, entrepreneurs. The young generation, the new generation who are going to adopt this particular concept of technology, they will be coming up with a new innovative product and they will be coming up with OEM and they will try to supply the logistics with the supply chain attitude to the global companies that may take place fasterly because these are all the lacunas we have in the past. That's why it is not happening. Now, the colleges also, technology is also available virtually. People are adapting, buying the things, and they're learning it, and they're going it. The new youth entrepreneurs are going to come up, which is happening in certain software side, and definitely in the manufacturing side also it will come up. That is optimistic point of view. We can see it because it is accessible now. Because I have seen one company in Vizag, they are coming up beautifully. They adopted all BITS people and IIT group of people. They started 3D manufacturing, 3D printing machine, and they started laser cutting machine. They started, and they're coming with a tailor-made product designing and batch part. That way they're starting it now, and they're supplying to globally. And slowly, the mass production, if they want to go, depend on the supply chain and deployment, it's that type of product, that type of entrepreneur model, we have to copy it and adopt it, and definitely it's going to happen. And there's a possibility that our young generation, new generation will adopt faster, and it is available. The technologies are available now, and everything is available in the net. People can learn it and do it what is needed for the globally. And that's the thing, government is also looking to help them, and definitely they are going to adopt that. The older generation of our trend, it is very difficult to come out and then change our things. Maybe it's my point of view. I'm just looking it and saying it.
I will leave one thought, sir, here. So in Indian scenario, a 300 crore company still working on Excel sheets and Tally.
Okay.
Okay. Yeah. So we have to first understand the baselining of, I'm not talking about the new companies and youngsters coming and starting 3D printing and starting, even some companies started manufacturing digital baby diapers. That is a new manufacturing and all. Okay, but I'm not talking about that. The 40% of GDP or 37% of GDP is coming from MSMEs today in India, still living on Excel sheets. Still, they don't have basic enterprise resource planning, CRM, supply chain things and all. Before I even talk about product engineering, so one is the process and other is the product engineering. So both aspects needs to be looked at differently. We need to really look at how the economy of scale, that means 100 companies coming together, okay, their non-mission critical processes are their HR. Why every company has to spend? There might be a platform available and you rent it and share the price. Or I will, the governments or some of the professional bodies can work and set up, as you rightly said, a digital twin center of excellence.
Yes.
Rent it. The MSME can go and rent it for 1 month, 2 months, 3 months.
These all strategies definitely, I think, be taken up. They will be taken up because the cost point of view, competitive point of view. Like earlier we were not aware about all this. Now at least we are aware. If you take a small example about sports, earlier badminton we don't have anything. We are nothing. Now we have an academy and they're trying with our people are global players. Even if you take cricket also, in the sports point of view, roughly, because we are generally talking about it. Now, youth is also aware because of internet technology 4G or digital 4 and digital 5, industrial 4, industrial 5. These are all the new modes, and this is where you can access and you can learn. Self-learning and adopting. No doubt colleges also adopt it, or if they can go online in global education and they can learn it. You not to be local college and all that. They can go to global education and they can learn it and they'll adopt it. And this is going to happen. They have a tie-ups. We can have a tie-up with the people. And then if the thing is ultimately, if you are able to adopt it and do it in India, they will welcome it. Like how we did software. We are adapted ourselves to the technologies and we are supplying and giving the services. Even today, latest blockchain or the metaverse, anything you call it, our people are going to adopt and do it. And that's why in this phenomenon also, if they are aware and they learn it, they will do it. No doubt. The capital expenditure, how to do it, a risk-taking capability, there will be various strategies. One person will do, or a group will do, or exchange of the things we will do. They will be doing it. It's going to happen. There's a possibility. Optimistically, what I'm saying is that our information is available now. People can learn it, and people can adopt it for the competitive of global field. That's a possibility is there because of Industry 4 and 5. It is all cloud-based. It is all internet-based. It is all, everything is internet-based. We can adopt it.
Sir, the comments are I think, sir, I think we have already overshot the time.
It's not a problem, sir. Not a problem. Even I am also getting a lot of inputs from Rajendra Garu and VSR Garu. Yes, sir. Even not to speak about Industry 4.0, even ERP package undi. కొంతమంది ఇంప్లిమెంట్ చేశారు, కొంతమంది ఇంప్లిమెంట్ చేయలేదు. నేను 2011లోనే మా అబ్బాయిది ఇంటర్మీడియట్ ఫీజు కట్టడానికి వెళ్ళినప్పుడు one intermediate college was using ERP package and it is shared across their other branches also. They are doing. Even some of the big colleges, standalone colleges, they are not using ERP packages. మా స్టూడెంట్ ఫీజు కట్టడానికి వస్తే పాత రికార్డులన్నీ చూసి అప్పుడు ఇంత కట్టావు, ఇప్పుడు ఇంత కట్టాలని చెప్తుంటే నేను చూశాను. ఈవెన్ ఎస్ దట్ ఈస్ అగైన్ మెంటల్ బ్లాక్. అక్కడ ఏంటంటే వాళ్ళు ఏదో నడిచిపోతుంది నడిపిద్దాం అంతే.
It will be happening, sir. Today we are able to talk globally in web conference and everything, ERP information is also can be embedded. It is going to be not so complicated. Where technology will be easing out and the basic thing is the connectivity is coming up. So
unless you implement and then see in the line of even product life cycle, when you say only some people are given the option to edit information. If they are given the rights to edit and then update it, the updated information will be there in the server that can be accessed by everyone. So whoever is accessing, that is a single source. That's what I am trying to say. See, that is the greater advantage of Industry 4.0. Everybody will get the same information right from the shop floor to the top management. Yes, sir. Okay, sir.
I think you will.
Thank you.
Yes, sir. Thank you, sir. I think thank for the honor for asking me to propose a vote of thanks in the absence of my secretary who normally does it. It is always a pleasant job, which I always keep saying every time. Thanking all of you is a great experience, nice, happy experience. And most to thank Dr. G. Chandramohan Garu for his wonderful exposure for this industry 4.0, IIIT, as it's called. I think there's another name for that. And we are really, the country must get geared to go to this, and MSME sector, I think it must be far behind. So I think probably at the end of sometime later, probably somebody will get latched onto that. So I think thank you very much, sir. And probably we look forward to again getting back to you again, either offline or online again. And I also thank the organizers, especially Rajendra Prasad Garu for bringing on our platform. Our Treasurer Jeevan Naidu Garu, or Secretary Garu, and of course our President Kavita Garu always makes herself very vibrant. I also see our senior past President Ramesh Garu also namaste, sir, and thanks for coming. And other August audience who took the time to be present here, sir. Thanks a lot. Thanks for the organizers and to the Karthi. Thank you much, sir. Namaste. With this, we close today's session.
Thank you, sir. Thank you very much. Thank you, all of you. Thank you, Rajendra Garu, particularly for your all your efforts.
Thank you very much.
Thank you very much.
Ramesh Garu is, I think, doing fine, sir.
Thank you. Karthik? Yeah. Karthik?
Karthik, are you there? Thank you, sir.
No, madam, you're there. Please.
Thank you.
Add a few words.
Very much, yes. I was on a mute, so that's the thing.
Thank you very much, madam.
Good to see you, sir. How are you, sir? Ramesh Vemankanti Garu.
Yeah, absolutely fine.
You recovered, sir? Completely, you're fine now?
Absolutely, totally fine.
Great.
Ready for anything now for HMA.
Wow, that's amazing.
Thank you all, sir.
Yeah, thank you.
On the count of 5, I'm closing the meeting. Good day.
Yeah.
1, 2, 5. Good night.
Good night, sir.